Okay, everyone. So, hello, and let me tell you what's going on this week. So, I hope you all got my email. And today, what we're going to do right now is we are right here on the 10th, and we're a little bit behind. So, what I did was I posted right here on the calendar the first 3 pages of chapter 6. So if you didn't get my email about that, please watch that. All right, because we're going to start right now on page 34 in the notes and cover chapters 6 and 7. And then we'll try to do as much of 8 and 9 on Thursday. So now these pre-lectures I have due here at the end of the week. But really, ideally, I strongly recommend that you do each one of these pre-lectures before the lecture. So it's great if you've already done 6 and 7 for today. If not, try to do them all, or at least 8 and 9 for next time, before the lecture. I think it'll be more understandable to you. They're called pre-lectures, but we leave them till the end of the week. Also, I strongly encourage everyone to do the bonus survey that's up right now. And if you have any questions, like somebody does, go ahead, ask your question. Yeah, if the bonus survey just got posted this morning. Okay, so if you look for it before, just look for it again. So any questions on that? And as you see, you probably all know that we shifted the homework by 1 day. So tonight, homework 3 is due, which covers chapters 3 and 4 way back here. And this is the one that covers chapters 5 and 6. And I'll post this one after today's lecture, homework 5. Okay, so let's go to the document camera and begin. All right, so here we are on page 34, and actually, no, that I covered, sorry. We are going to start here on page 35, because this one was covered on the lecture that I posted. We'll go over it. Don't worry if you haven't seen that lecture yet. But this is where we're going to start on page 35. Okay, so let's look at this. So here we are. Today is Tuesday, the 10th. Now we're talking about here the multiplication rule. The multiplication rule. And what is the multiplication rule? It's the probability that 2 things will both occur. So why don't we just go to the summary right here and fill this in. All right, so the multiplication rule, and we're on page 39 now. 39. The multiplication rule is the probability that A and B are both happening, both occur, is what? It's the probability. I'll just write it down here. So we want the probability that 2 things both happen, 2 events both happen. The probability that A and B both occur. That's equal to, it's multiplication, the probability of A times the probability of B. But you have to be a little careful here because you want both of them to happen. You're trying to get the probability that both of them happen. So this is the probability that A happened times the probability that B happened, given that A already happened, given this is true too. You can think of them as just statements, true, false statements. So the probability that A is true times the probability that B is true, given A is true. Now, so it's really, even though there's an and here, it's the intersection. It's both of them have to occur. So that's why you're multiplying probabilities. You're not adding them. Some people get confused because of, all right, but we're multiplying it. The probability of getting a head on the first flip of a coin is 1/2. And of those, if you got ahead, then the probability of getting ahead again would be half of those. So it's half of a half, which is a half times a half, 1 out of 4 ways to get 2 heads on 4 tosses. Okay? So it's times here. Now, if the 2 events are independent, what's that? That comes up all the time in statistics. Independence. 2 events are independent. That means if the probability of one event happens, doesn't change the probability of the other one happening. It has no effect. So knowing one thing happened doesn't tell me anything about the other. For example, like I think your height and how well you do on Stat 100 exams are independent. Knowing your height doesn't tell me anything about how well you're going to do on the exams. All right, so if they're independent, then the probability of A and B is equal to the probability of A. It's still the same thing, but we can shorten it by saying this. We can say it's just equal to them multiplied together, because the probability that B happening given A, well, A has nothing to do with it. A gives us no information about B, so it boils down to that. Why? Because the probability of B given A, if they're independent, A tells you doesn't change the probability of B. It keeps it the same. So this is equal to that. Okay? So, and we're going to give an example of independence. An example would be sampling with replacement. So an example, for example, independent, we'll look at those in a minute. We'll look at cards. If I brought a deck of cards, let me just check to see if I did. I thought I did, but maybe not. Hold on a second. Yeah, I did. Yay, we bought some cards, so we can look at that. All right, now, the other thing I should probably go over that's going to come up is that the probability of something happening and the probability of it not happening is equal to 1, or 100%. Okay? So the probability of getting ahead on one flip of a coin plus the probability of getting a tail is 100%, because either you get a head or you get a tail, right? So this is, so the probability of A happening plus the probability of it not happening. If an event either happens or doesn't, then like a true-false statement, it's either true or false, then this is called A complement is equal to 1. Okay? And so let's go to our examples now. Back on page 35. Okay. So we're going to look at cards here. And remember that rule I just said, I just told you, and let's start with this one. What's the probability of drawing 3 cards from a deck with replacement and getting all hearts? Okay, so what's that probability? Let's look at the deck of cards, okay? So we're just saying the probability of all hearts is equal to what? We're going to multiply the probability of a heart on the first card times the probability of that's a heart, times the probability of a heart on the second card, times the probability of a heart on the third card. So it's going to be these 3 probabilities. Now, there's 52 cards in this deck. So I should probably say that somewhere if you don't know. So there's 52 cards total. I guess everybody knows that, right? There's 52 cards total. There's 4 suits. What are the 4 suits? Hearts, spades, clubs, and diamonds. And then within each of these, there's 13 cards. There's 13, and there's 13 cards within each suit. So 13 times 4 is 52. Okay, So for this one, there's like 2 through 10, and then there's a jack, a queen, a king, and an ace, and that's true for all of them. All right, so that's your deck of cards. They look like this. Okay, so now draw 3 cards. Okay, so I'll draw the first card, and there's 52 cards total. So what's the probability of a heart? Well, there's 13 hearts, right? Let's see. Well, I got a heart, right? I'm getting all hearts there. So the chance was 13 times 52, right? Now I'm going to put that heart back. I'm going to put it back. So does the deck have a memory? Is it going to remember anything? Is getting a heart on the second one independent? Yeah, it's not going to change. My chances are still going to be 52 out of 13 times 13. My chances are still going to be 13 out of 52 times 13 out of 52. So it's just easier to write 13 out of 52 cubed. And it's independent because the chance of getting a heart on the second is the same as getting it. It doesn't change because the deck doesn't change. All right, now about what if we do it without replacement? Okay, so this was with replacement, and now without replacements. So we're going to do the same thing, the probability of all hearts, but now it's going to start off the same way. The chance of getting a heart on the first one, you have 13 hearts in here out of 52 cards, but after you get the heart, you assume, okay, so let's say we got a heart, and we're not going to replace it. It's without replacement. So now you want the chance that the second is a heart, given this was a heart and that it wasn't replaced. So now we have how many cards left? 51. And then how many hearts do we have left? 12. Okay, so then the next one, okay, so that assumes we get another heart. The next one, what's the chance? Because you want the chance that all 3 of them are hearts. So now we only have 50 cards left. I took 2 out. And how many hearts are left? 11. Does everybody understand that? So without replacement, whenever you see without replacement, the chances change. So the events are dependent, whereas with replacement, they're independent. So it's a really easy example to remember what independence and dependence means. Now let's move on to what's the probability of drawing 3 cards from a deck with replacement? So we've got with replacement. And okay, so this was getting all hearts, and this is not getting all hearts. Not getting all hearts. So what's that? Well, let's see. Not getting all hearts, the probability of not all hearts. Well, you know, this one's kind of hard to figure out directly because let's look at it. Not all hearts. What are the possibilities on 3 cards? You draw 3 cards and you could get no hearts, 0 hearts. You could get 1 heart. You could get 2 hearts, or you could get all 3 hearts. And we figured this one out. That was easy to figure out. This was the probability of all. Now the probability of not all is not just none. These have to all, the probability of all means any one of these 3 possibilities. That's the probability that we have to figure out. And if you do it directly, it's kind of hard because think about it. This was easy. There's just one way to get 3 hearts, right? You get a heart on the first, a heart on the second, and a heart on the third. So you can multiply those probabilities. But look at all these ways. Well, this one's also easy. There's just one way you could get no hearts. We could get no hearts on the first, no hearts on the second, and no hearts on the third. But what about these? Like this one's more complicated because if you just you could get a heart on the first. There's 3 ways actually, because you could get a heart on the first, a heart on the second, and a heart on the third. So a heart on the first and have no heart on the second and no heart on the third. Or you could have it just the heart in the middle, or the heart being the last one. That's 3 different ones. And same with 2 hearts. That's heart 2 because 2 hearts means 1 not heart. So that's 3 ways as well. You could have the not heart on the first, the second, or the third. So you could figure out all these. When you see not all, think, oh, do I want to do all that work? No, there's a much easier way to do it because these are complements, not all and all, right? We encompass all the possibilities. You either have all hearts or not all, and they're going to always sum to 100% or 1. So it's much easier. This way, think of it this way. This is really hard to figure out, whereas this is easy to figure out. So if you want to figure out the probability of not all, you don't go direct. It's very hard, and it will take you a lot of time, and you're likely to make mistakes. If you did it correctly, you'll get the right answer. But why not just do it the easy way? They have to sum to 1, so just say it's 1 minus the probability of all. So that's the easy way to do it. Okay? So that's what we're going to do here. So the probability of not all is going to be 1 minus the probability of all. Well, we already figured out the probability of all right here. So that's going to be 1 minus 13 over 52 cubed. How about this one? This again. This is the probability of not all. Not all. Here, I'll just probability of not all. This was the probability of not all too. Not getting all hearts. Well, so the probability of not getting all is going to equal 1 minus the probability of all 3 being hearts. Well, but now you have to be a little bit careful and notice that it's without replacement. So it's 1 minus, we actually already figured out that probability of all without replacement. It's right here. It changed, so we could just put that here. 13 over 52 times 12 over 51 times 11 over 50. And our homework program is really nice. Instead of, you can just leave it in this form. In fact, you should leave it in this form because answers can be really close together, and I don't know if you're right or wrong. It's much easier for it to grade. Otherwise, you're going to run into rounding issues. So just leave it in this form. Don't put it into the decimal form unless you're asked for it, okay? And on the exam, we'll do it the same way. That way I can just see if you have the logic and I don't have to worry about calculator errors or getting very, like what if you accidentally, it's not going to be much different if you put a 51 here. It's wrong, like 52, 51. But in the, rounding, I wouldn't be able to tell. This way I can tell that you understand what you're doing. Any questions on that? All right. So now, I was going to have you do iClicker questions on these, but I'm sorry. Everybody's going to get points for today for your iClickers, but it won't, because I didn't download your grades yet. I can't start a new session. I forgot to download your grades from apparently I can't. Usually I can, but maybe with this software I can't. So I apologize, but everybody is going to get credit. Okay, so it's one of those days where everybody gets credit. There's 29 lectures. You get, so this will just be one of the free ones. Yes? Oh, good question. Her question was how on the midterm or on all the exams that feature questions like this, actually all the exams are multiple choice. So I will give you different options. All right? So ones that look a lot alike, Like I could ask this question and give you all these options or something, and you'd have to pick the right one. Okay? All right, so now let's look at this one now that we did that one and just make sure that we can do it. Okay, so what's the probability of drawing 3 cards with replacement and getting no hearts? No hearts is not the same as not all. Remember, no hearts is this situation. It's easy. And not all is that situation. So these, by the way, are opposites, which is different than complements. This is all and not all do not encompass all possibilities. All and none, excuse me. All and none, right? All and none. These are the 2 easy ones, all and none. All right, so let's look at this. All right, getting no hearts. Well, we know that's easy. The probability of no hearts, because there's just one way to get it, is equal to the probability of no hearts on the first times the probability of no hearts on the second times the probability of no hearts on the third. Now it's so what's the probability of no hearts? Let's think about it. There's 52 cards, and how many are not hearts? 13 are hearts, so the other 39 are not hearts. That's 13 spades, 13 clubs, and 13 diamonds. You add them together, that's the 39 cards that are not hearts. Now, so if you were doing this, I know I like cards, so pick one out, and it's not a heart, but we put it back in. So that is independent. Our next draw is completely independent. Doesn't matter what we got on that because we replaced it. So it's going to be the same for all 3. So that's our answer. That's easy, and it's independent because it's with replacement. All right, now how about if it's without replacement? We're going to do the same thing we did before. So we're going to say the probability of no hearts. It starts off the same. The first one is 39 out of 52. There's 39 cards that aren't a heart. Whoops, I got a heart. Try another one. Whoops, I got another heart. There. Okay. So I got that's 39 ways to do that. But now it's without replacement, so I'm leaving that out. Leaving it out. Okay? So now the probability that I get, now there's only 51 cards, and the probability that I don't get a heart, given that one's still out there, now there's only 38 of them. Do you see? Everybody understand? Right? And then, got a club, and now there's only 50 of them, and there's 2 not hearts out there, so there's only 37 left in the deck. So that's my answer. All right, and now, what's the probability of drawing 3 cards with replacement like that one and getting at least 1 heart? At least 1 heart. Well, that's another tough one. Let's look down here. Here's not all. Let's do let's just write this over again. Okay, so we could get 0 hearts, 1 heart, 2 hearts, or 3 hearts. All right? And at least 1 is all of these. At least 1. That's 1, 2, or 3. And so it's everything but none. Right? So none plus at least 1 equals 1. Okay? Not, right? So we could do the same thing. There's 3 ways. 3 ways. We don't have to write them again. There's 3 ways. And there's 1 way. And this none also has 1 way. So these 3 are hard. So when you see at least 1, don't subject yourself to all that. It's a lot of work. Instead, use the easy way. because remember, okay, use this. So the probability of at least one is very difficult to figure out, just a lot of work to figure out directly, especially if you have 4 hearts or 5 hearts, then it gets really hard. So instead, use this, and it's equal to 1 minus the probability of none, or no hearts. Okay? So we're going to, these are complements, and these are complements. So if you see at least one, do this. Let's do it then. So the probability of at least one heart is equal to 1 minus the probability of no hearts. At least one heart. Okay, so what's that? That's 1 minus, it's with replacement, it's just going to be that. 39 over 52 cubed. It's all the other ones. Any questions on that? Okay. At least one is hard. At least 1, 2, 3. Everything but 0. All right, now let's do the next one. What's this say? The probability without replacement, so that's going to be, probabilities are going to change, and here we're getting at least 1 again. Okay, so we know how to do that. The probability of at least 1 heart is equal 1 minus the probability of no hearts again, and everything's the same except it's without replacement. So it's going to be 1 minus, it's that right there. Okay, 1 minus 39 over 52 times 38 over 50. Oh, that's hard to write. Here, I'll do it over here. So it's 1 minus 39 over 52 minus 38 over 51 minus 37 over 50. It's all that. So, any questions on all that? So I think, yes, there's a question.
Is it minus or times?
Oh, of course it's times. Did I say minus? And I wrote it. Thank you so much. I really appreciate that. I know a lot of you probably noticed that, but she had the, she took the initiative and corrected it so everyone's notes are correct, because I know a lot of, any given time, people are just copying, and I really appreciate it. Thank you. Thanks a lot. Please help me out that way. Okay. So, let's turn the page. And now we're going to do some conditional probability. Okay. So, we just talked about conditional probability. Really, we did. We said that the probability, the conditional probability of an event B is the probability that the event will occur given that A has already occurred. Probability of B given A. We just saw that, okay? So now it gives you this right here, but this really directly follows from what we just did. This follows from what we just said. It follows from the multiplication rule. It's just rearranging the terms. Why? Because the multiplication rule says what? The probability of A and B is equal to the probability of A times what? The probability of B given A. And now all we did to get to that is divided both sides by the probability of A. So you get the probability of B given A is that over, so it's the same thing. Can you read that, by the way? It's kind of messy. It says the probability of A times the probability of B given A, right? Y'all know that? So just a different way of rearranging it. And I always like pictures. especially when it comes to probability. So we could think of it as, let's do the picture. So you could have A. It's really, okay, so the probability, so you have some set A here. And then you have some other set B here. And right, the probability of A and B is the intersection. So if I colored this all A yellow, and I color all the B blue, blue plus yellow should turn to green, did it? Can you see that? Yeah. So the green part, I'll make it greener, right there, that is the intersection. That's the probability right here, the green part, is the probability of, that's, well, I'll just say it's A plus B, right? Or another way of writing that is A intersection B. It's both A and B right there. So now this really makes sense. The probability of getting B, B is all this, all the blue part. But once you get into the A, given that A has happened, B is just this green part. It's the part that's both blue and yellow, green. It's right in here. So that's saying this, the probability of B given A, is this little sliver divided by the probability of A. Does that make sense to see the picture now? And what would be the probability of A given B? That would still be the intersection. That would be the probability. That would still be the probability of A and B, this part. But now it would be given B. So you'd start with B. Given that B had happened, what's the probability of having A plus B? So it would be this little sliver over B. So that's the idea. All right, let's do an example, and we'll see how you can keep that picture in mind. Sometimes it's easiest to do tables when you have two events here, like two conditions, two or more conditions. All right, so let's read this. Suppose a box contains 30 aspirins and 70 Tylenols. All right, so you have this table here, and the total number of aspirins is 30, and the total number of Tylenols is 70, and that means we have 100 altogether. So that's what we know from that piece of information right here. Now it also tells us about the poison. Half the aspirins and 10% of the Tylenols are poisoned. All right, so to fill in this middle section here, okay, of the 30 aspirins, half of them, 15 are poisoned. So that means 15 are not poisoned. And of the Tylenol, it says what? 10%. So 0.1 of the 70 are poisoned. So that's 7. That means that 63 are not poisoned. All right, so now we can get the totals here, and that's 22. There's 22 poisons altogether, and there's 78 not poisons, and of course they should all add up. All right, now if we want to figure out the probability of drawing a pill from the box and getting a poison from the whole, okay, so this is just saying what's the probability of a poison out of all of them, right? So out of the 100 total, how many are poisoned? 22. All right? Now it says, what's the probability of randomly drawing a pill from the box and getting a poisoned aspirin? Poisoned aspirin. So what is this saying? The probability of getting poison and aspirin. Well, there's an easy way to do it just by looking at the chart, right? We could do it that way. We could do it that way first. Poison and aspirin is right here. These are the ones that are both poison and aspirin. And That's 15 out of all of them. That's the total. But another way of doing this, we could have said, or the probability of getting poison and aspirin, right, is the probability of poison times the probability of aspirin given poison. All right, so we could do it that way. We'll get the same thing. The probability of of just getting aspirin is 22 out of 100. And then, the probability of poison, poison, this one, is 20. This is I'll put it right above it. So this is 22 out of 100. And then I want to multiply that, by the probability of aspirin given poison. So given them in the poison, out of those 22, 15 of them, of the 22, are poison. It's kind of hard to do, but I just wanted to show you get the same answer. It's easier just to look at the table. I just wanted to show you get the same answer. All right. Now, so if somebody randomly draws an aspirin, there's a 50% chance it's poison. Does that mean, so it says the probability that it's poison, given that it's aspirin, is equal to 50%. That's what it's saying. Does that mean that the probability of aspirin given poison is also 50%? Well, how'd they get this? This is the probability of poison given aspirin. What is that? Given that it's aspirin, we're just saying, given that here's the probability, it's 15 over 30. That's the probability of both over A, right? And here it's asking for the probability of both. Remember, this is the probability of the intersection of A plus poison over the probability of poison. So that's 15 over 22. Whereas this one was the probability of 15. This one right here, this is the same thing. It's the probability of aspirin plus poison, but it's over the probability of aspirin. So that's why they're different. Because here it's 15 over 22, and here it's 15 over 30. Okay? Does that make sense to everybody? Or is that confusing? Raise your hand if it's confusing. Raise your hand if it makes sense. Cool. This hardly ever makes sense to people. You guys are on top of it. All right. So basically the idea is, in both cases, probability of A given B and B given A, you have the same numerator. You have that intersection. And they're different when the probability of A and the probability of B are different. Otherwise, they'd be the same. So if these were both 30, they'd be the same. But when they're different, probability of A given B is not probability of B given A. Okay, some definitions here. This is a contingency table, an example of a contingency table. And you have these totals out here. They're called the marginal probabilities. The marginal probabilities, like for example, the probability of an aspirin or the probability of a Tylenol, these are marginal probabilities. And in the center here, these are called joint probabilities because all four of these numbers over the total here, they give you the probability of two things both happen. So in all contingency tables, the numbers in the margins are called marginal probabilities when divided by the overall total, and the numbers inside the cells are called joint probabilities when divided by the overall total. So I'm going to cross that out. Your answer to which above is a marginal probability and which is a joint between A and B. Okay, well this one is a marginal because it's in the marginal. So that's the marginal one. because it's just saying the probability of a poison out of all of them. And this is saying the probability of jointly being poison and aspirin out of all of them. That's this one out of that. So that is a joint. So we can fill that in, A and B. And because this probability B is joint because it's the probability of getting both conditions jointly. So that's both A, aspirin, and a poison. All right. Now, part C was an example showing that the probability of A is not the same as the probability of B. And you understand. It's here's a, can you think of a really obvious example? Go ahead. There's a question. Yeah. Yeah, over the total. Otherwise, it's a conditional probability. Okay. Now, part C, her answer was for the joint probabilities, it's all over the total as well. These ones like 15 over 30, etc. These were conditional probabilities. Okay, now we're going on to part C, and it said, can you think of a really obvious example? Because people always think, oh, the probability of A given B is the same as the probability of B given A. But here's a really easy example to remember. Okay, so the probability of being a man given you're human is not the same as the probability of being human given you're a man. Because when you think of the picture, okay, so there's about a if you're given that you're human, there's about a 50% chance that you're a man. But given that you're a man, well, do you think all men are human? Maybe some people would disagree. Some people have met, oh, God. But I'm not going to go there and say anything. Let's just say this is 100%. If you're a man, you're human. I mean, the picture's pretty obvious. You have all the humans, and men are completely contained within it. So, just to keep it straight, when is the probability of A given B equal to the probability of B given A? Now remember the definitions. Probability of A given B, we're just using this. Probability of A given B is the probability of A and B over the probability of B. And the probability of B given A is the same thing. It's that intersection, A plus B, but it's given the probability of A. So when are they the same? It's going to be what? When probability of B and A are the same. When these are the same size, A and B. They'll be the same. So it's an easy way to remember it. Okay, so now, let's see, we can do some more of these conditional probabilities because you have a bunch of them in your homework and they come up so often. So, here's, do you want to skip this one and do it on your own, or you want to do, how are you feeling? Are you feeling comfortable about these, or you want me to go through them all? Go through them all? Raise your hand if you want them all. Raise your hand if you want me to skip some of them. Skip this one? Okay, how about I just do this AIDS one then? So we're going to skip, but it's okay if I skip it. This is like a homework one, but there's a little lesson inside the homework. You can just click on it and see. Okay? All right, so we'll skip this one for now. And I can give you the answers just to make sure you got it. Why don't I just fill in the table and you can figure it out on your own real fast without explaining it. How's that? Okay, so what do we have? Just pretend there's 100 people total, okay? And then fill in 9, and what do you want to do? 80% are guilty. So fill that in first. Fill the column in, always fill this column in first. So this is just the quick and easy way of doing this. Okay, 80% and 20% are not guilty. All right, then you have this other thing, 95% of the time. All right, 95% of the time they're making the right decision. So if you're innocent, you want to be acquitted. So 95% of that 90, what did I say? 80% are guilty. Boy, I did it fast and I screwed that up, right? Didn't it say 80% are guilty? Okay, so 95% of 20, that would be 19, but only one gets wrongly convicted. I'm looking at this right here. And then if you're guilty 95% of the time, you want 95%, that's the right decision, right here. So that would be 76. That would be 4. And then you would add them up. And then you can fill out the chart. Okay? How does that make, does that help? And then here's the, I'll just quickly do this. And this one is asking what? The probability of convicted if you're innocent. So you just look at the innocent people, right, out of the 20, one's convicted. Whereas the probability of being innocent, given you're convicted, there's 77 convicted and only one innocent, so they're not the same. All right, so there's that. Now this one's a really cool example. Let's just, because this happened to me, not with AIDS, but with breast cancer mammograms. And so I got interested in this type of diagnostic stuff. All right, so let's look at the facts here. This is true about this test that was widely used called the ELISA Test. All right, what does it say? That 99% true positive. So ELISA is a really good test. 99% of the time, if you get a positive test, if you have AIDS, it's going to 99% of the time correctly. So these are 99% true positives. If you have AIDS, it's a true positive. You'll just about always, you'll get a positive result. But there's also 6% false positives. So if you don't have AIDS, 6% of the time, you're going to get a false positive. All right. So, and about 1% of the people who get tested for it's usually used when people are giving blood, and about 1% of the people who give blood have some AIDS virus in them, in the people who are giving blood, in the data that I looked at. Okay, so about 1% of the blood samples are truly contaminated. All right, so now you know this, and just show of hands. So somebody, you don't know anything about this person, they come to you and say, hey, I got a positive result. I went to give blood, I got a positive result for AIDS. What are my chances of having AIDS? Okay? What would you tell them? What would you think? Do you think the chances are over 50%? Raise your hand. Do you think they're under 50%? Raise your hand. You don't know. It looks like a really good test. Wouldn't you be scared? You got a positive result, wouldn't you be scared? Okay. So most people, even doctors, when you ask them this question, overwhelmingly get it wrong. And they think, hey, it's a great test, and chances are very high. Like most, over 90%, a lot of them think. But, I mean, when they ask them, seriously, because intuitively, that's what you think, because you're thinking, but what do you know? All right, here's the intuition. Here's one way of intuitive explanation is this. Okay, 100 people. If you have 100 people, how many have AIDS? That piece of information that only 1% has AIDS is really important. So only one has AIDS. So out of 100 people, there's one person who has AIDS, and there's 99 who do not have AIDS. Now, the person who has AIDS is 99% likely to get a positive result. So this person will get a positive, right? 99% of the time will get a positive. So this person, you have one person has AIDS, so this will be one. This person will get a positive result almost all the time. But of these almost 100 people who don't have AIDS, 6% of them, 6 of them will also get a positive result. That's the 6% false positives. So this is the 6 false positives, and this is the 1 true positive. So now you want to know the probability, of having AIDS given a positive result, right? Probability of so the person got a positive result. There's 7 total positives. But his chance of really only having AIDS is 1, because there's only one true positive. So the picture is this. What's the picture is that there's just here, that this right here, the probability if you have AIDS, right, the probability of testing positive is 99%, right? That's 99, that was given to us. That's 99%. And you're getting that mixed up with the probability of AIDS given positive, which is much less. If we wanted to figure it out exactly, we could take 100 people here, because I approximated here, all right, 100 people, and then one of them has AIDS, that's the 1%, and 99 don't. Now, 99%, 0.99 of that one, that's going to be, so that should really be 0.99 there, right, are going to test positive, and only 0.01 will test negative. Now here, when the blood does not have AIDS, right, how many positives are we going to get? We're going to get 6% of the 99, which I approximated at 6, but it's really more like 5.94. So then this has to add up to 99. So the rest, the 90, this will be 93.06. Okay, so we can do the totals. And this is 6.93. So if you wanted it to figure it out exactly, this is an approximate, so exactly it's, so this is approximately equal, would be what? It would be, what we're looking at is we want this over that. And that's where we got the 1/7. So it would be 0.99 if we wanted to figure it out exactly over 6.93. Does everybody understand that? Yes. You're missing, the right is this way? 0.01 is, this is a 1, not a 0.1. That was a dot. Gosh, so easy to do. Okay? All right, so now the picture would be something like this. What? We have two events, we have AIDS and we have positive. Only one person has AIDS, and there's 7 positives, so it would be like 7 of these positives, and then one of them has AIDS, right? We're really 0.99, so there's a little speck outside there, but that's the AIDS. That's 1, so that's the AIDS. So it's really like 1/7 versus it's really 0.99 over 1. This is really, this is, if you can look at it here, it's 0.99 over 1. Okay, so that's the idea. And so it's very useful. It came in, I mean, when I go to I just tell you a quick story about how useful this is whenever I go to a doctor, and I always mention that I'm in statistics, and they change their story completely. I mean, all of a sudden they're saying, well, giving me all sorts of uncertainties, to the point where I went in for my back because I'm having these back problems, and this is a true story. Once I said that, you know, I took all these x-rays, I had CAT scans, MRIs, all this stuff, and he was trying to